This is only made out of wool.
And okay, remember we're going to be streaming from now, okay? Awesome. Hey everyone. So today's going to be an interesting one. There's been some discussion on Twitter about concurrency and issues with Puma. Let's just find that. Not that one. Not that one. Here we go. Nate just said, if you think switching to a different application server is going to make a difference, I've got news for you. And I just replied, I think Falcon can do something a bit more exciting. And then I got asked if I had compared Falcon and Unicorn, which I haven't. So I started doing that and ended up down this giant wormhole. So it's a pretty interesting topic because there are so many different angles you can take. And today I'm just going to try and look at... I found some interesting issues with work, like the benchmarking tool work, and how it reports latency. I'm not completely sure if it's correct, so I made a fork, and so we'll have a look at that. So the first thing I'm going to do is I'm going to have a look at...
Jumped over the couch.
that's my daughter singing. We're going to have a look at this test harness I've got called Falcon Benchmark. And so this is a test harness which
No zombie. No zombie. Please zombie. Because I'm in survival. Please.
this is a test harness which pulls in Puma, Falcon, Passenger Standalone, and Unicorn, and just throws them all together with there's this config.ru, and that file you can put whatever you want in here and it will run it on all those 5 application servers, and then you can hit them and see what the response rate is with light latency, requests per second, whatever you want really. So it's pretty useful. So let's go ahead and set that up now. So I've, earlier I already generated the images, but there's a rake task here which does all of that. You basically just go rake setup, but it's a little bit pointless to redo that all now. So we're just going to start the images. So that just spawned up 5, I guess they're KVM images, kernel virtual machine, I guess. I don't actually know how they work. So we can see they're running there. And we can query them. So if we want to hit Unicorn, so the benefit of this is that all of these are running the same configuration. They're all running an identical operating system image. Everything is basically identical except for the specific application server. So it's quite a nice test harness to use. So what I was really interested in is how these servers respond to changes in concurrency. So work has this nice command line option called -c. There's a number of connections it makes. So if we hit, let's hit Puma. Now this is, on my computer I have 4 cores and 8 hyperthreads, so it's running 8 processes. Actually, that's not entirely correct. Is it running 8 threads? I think I put Puma into just the normal 1 process, 1 thread per... Actually, no, let me double check. Let's have a look at how it's currently set up. So Puma, so it's got 8 workers and each worker has 1 thread. Okay, so that should give us the best level of parallelism because there's 1 process per CPU core or per CPU thread. And then because it's C Ruby, we don't want to have any contention within the interpreter, so we just have 1 thread. Okay, right. So over here, we can specify 8 connections and we use 8 threads. That means 1 connection, like 1 client connection per thread. And let's just make this a bit quicker because otherwise it takes too long. Awesome. So that's pretty quick. It's less than a millisecond. Now there's actually another benchmark called blocking. Let's have a quick look at how that works. Basically, it calls kernel sleep for 10 milliseconds. So if we run this, we expect the latency to be pretty much 10 milliseconds, which we see it is, which is good. That's what we expect. Now, when I was trying this out before, I noticed something really strange. There are 8 threads, like 8 processes and 1 thread per process. So if we double the number of connections, we would expect 8 of those connections to connect to the 8 processes, and then the 8 other connections would connect, but they would be waiting until the first 8 had finished. And so our latency should go from like 10 milliseconds to, I don't know, like 12 or 15 or something. It should be a little bit slower. But what I noticed with Puma is it doesn't matter what you change this to with work. The latency, in this case, is absolutely identical, 10.59, which is pretty pretty specific. But even if we change this to like, I don't know, 128, we still have 10 milliseconds of latency, and it just doesn't make sense. So I wasn't really sure why this was happening, and I think basically there are issues in the way that work computes latency. So let's have a look at the work source code and find out what's going on. Should I just add in here? So I've already made some changes. We were using the normal work supplied by the operating system, and I've got a custom build here which we're going to start using. But let's have a little bit of a look at the changes I made and why. So the way that work works is it basically spins up a bunch of threads, and each thread has a number of connections. Then it uses an event loop, to run those connections as quickly as possible. And so that's the main event loop. And then once that's done, it will come out here. And what I've done is I've gone through all the connections and I print out how many requests there were in total and how many that particular connection completed. And what's really fascinating is when you start looking at this number, you start realizing something is horribly wrong with Puma's handling of requests. So let's I was going to look at the master branch, but I think we'll just leave it. Okay, let's build that. So now we have a local version of work, and let's hit Puma. So we'll just hit it with 8 connections. I ran it for 10 seconds. So that looks really okay. We have 10 milliseconds of latency, and there were 8 threads or 8 connections, each thread with 1 connection, and they basically service the same number of requests each, like 945. I don't know why. Actually, that's wrong. That's actually not the total number of requests. It's the total number of requests outstanding. Let's just get rid of that. And so that looks reasonable to me. The problem starts to become apparent when you change this to 16. Right, so what you see here is there were 16 threads with 16 connections, 1 connection per thread. They all connected, but only the first 8 actually serviced any connections. Now, what I actually have done is I've modified, so this particular build of work, I've modified it so that when the duration expires, because there's a timer, like for 10 seconds in that last run, when that duration, when it expires, it actually tries to gracefully finish all the requests. So that's why these ones here have 1 out of 0, because actually it would have been 0 out of 0, but what happens is those first 8 threads, they get told to stop. Actually, all of them get told to stop. Then once that finishes, then those 8, they're also trying to finish, but finally their request is accepted and they get a response back. So they finish off just their 1 request. But if you don't do that, like work doesn't take into account the latency, because work only takes into account the latency of completed requests. So the previous build of work, it basically didn't have any of that stuff and just had. So that's a Boolean value that gets set to true if the timer has expired. So let's build work again, and we'll try. I'm just going to set the duration to 1. It's kind of annoying. And I might actually need to change one more thing. So this is the reconnect socket code, which was gracefully stopping. So all of the stuff I did was just kind of a hack to make it work. God, this application has a hilarious name. Everything becomes funny. Okay. Hopefully this gives me the results I'm after. Right. So this is the normal way that work executes. Basically, a whole bunch of connections process no requests, and therefore the latency of that is never considered. Which means that actually in this case, I don't know why it's that. I think I'm running half of what I did and half of not. But basically, work will not report on the latency of incomplete requests. So even though Puma is not responding to any more requests than its number of processes, work still returns the latency of the request that it is handling. So it's kind of giving you like a pretty, from what I can tell, it's giving a pretty wrong picture of the actual performance. So when you do this graceful shutdown, then one request is completed for those connections. So the latency for that request becomes like whatever the duration you specified the test to run. So if we make that, then it's just like 128. So now what you see is the latency of this becomes 333 milliseconds, and that tries to be representative of the latency of all the requests in order to actually complete the one request per connection for all the connections that started requests. If we just go back to the normal build of work, we'll see that the latency should be reported 10 milliseconds, which just to me seems totally wrong. I mean, like, it's not wrong in the sense that the requests that completed had 10 milliseconds of latency. That part is correct. But that latency is not representative of the 120 users whose requests were just infinitely blocked by the 8 users who had their request serviced. So, yeah, something is wrong there. I guess the most basic solution would be like round robining. I don't know, like, how Puma works internally, how it's like handling those requests. But, you know, something is clearly not quite right. So let's have a look back at the test harness. So one of the useful parts of this test harness is a benchmark tool, which will basically run it will sweep a whole bunch of different concurrency levels and report on latency and throughput. So let's, I already ran this earlier, so I don't really know if it's a good idea to run it because it takes ages. That data is all there already. So let's just have a look at the results of the data, because that's pretty interesting. I got sick of using new plot, so I just decided to use chart.js, which to be honest isn't that great either, but it's better than nothing, I guess. So the bottom axis is the level of concurrency, and this left-hand side is the request per second. And this is for the small response, so that's the rack middleware that we looked at earlier. So this scales pretty nicely, I guess. I don't quite know why it's choppy up here. It could just be on my computer. Since I'm running both the server and the client on the same machine, it's not really that great. This curve shows the latency, And the latency is on the right hand side here, so we get up to about 15 milliseconds, 14.8 there at 512 simultaneous connections. I think that's a pretty nice curve, like it scales up pretty nicely. You look at that and go, there's no obvious like issues in terms of spikes or jumps or what have you. And then this line with the red circles, it shows like any errors reported by work. So like read, write, connect, any errors. That should always be 0. If there's errors here, what I noticed especially in the official release of work is that if there are errors, they don't take into account, they don't get taken into account from the point of view of latency. And actually I don't know if there's a B for that, but yeah, it's just basically errors totally throw the work stats out of whack. So what was pretty disappointing is passenger. I've been a huge fan of passenger for a long time until I saw this graph. I was like, wow. This is passenger running behind Nginx. And of course it's like the free version of passenger, so it scales pretty badly because it's, I guess they're just using threads. Or I don't know actually. The latency is pretty bad, like compared with Falcon, which was at 15 milliseconds. Passenger gets all the way up to 50 milliseconds. It's pretty nasty. Probably the worst part is though is the number of errors. I was really shocked when I saw this. So basically, at a certain point, I guess the buffer inside passenger or Nginx or somewhere in there gets full, and it just starts. It starts blowing out requests like crazy. There are more errors than like this is 22,000 errors per second. That's like corresponding to requests per second, and like the maximum number of requests per second we ever served was 13,000. So it's serving more. It's serving errors faster than it ever served requests. It's kind of funny in an ironic way. So let's just switch off Falcon. We'll focus on passenger. This is passenger standalone. It doesn't seem to have the massive dip, so maybe that buffering issue is inside Nginx. The latency is roughly the same, I guess. And it still has errors, but they're much less. So it's still suffering. It can't scale that well. Yeah, I was disappointed with those numbers. I sort of expected something better. Nginx itself is pretty awesome. Like I've benchmarked just static files in Nginx, and it can do like, on my computer it can do like 200,000 requests per second, no problem. So let's have a look at Puma and compare that with Falcon. So this is Puma not running in cluster mode. If you run it in cluster mode, then the performance characteristics change a little bit, and also some of this is actually, I believe it's still an issue with work. I don't know if it's the fault of Puma or not, because what you see is this, and that is quite a strange curve for latency. Let's just throw Falcon up as well. So Falcon is just like cruising along here. It's like, yeah, 512 connections per second. 512 simultaneous connections at a time, no problem. But Puma's up here with just like, over here it's 500 milliseconds. So I think what's happening here is work starts timing out requests. Now I can't, the work source code, these event-driven uses callbacks. Now, I've only been looking at it for like the last day to try and figure this stuff out. So honestly, I think this latency curve should just keep on going up, and this line here should just keep on going straight along. It shouldn't drop. I think it's a bug with like how work is computing that stuff. But yeah, it just does not look good to me. Like 500 milliseconds. So what's happening is that everything up until we hit the limit of the number of processes, the latency is absolutely fine. Like Puma is rock solid. But as soon as you get past the number of processes available to process to handle connections, latency just explodes. So that's probably a little bit concerning, I guess. Fortunately, the number of errors I think is really minimal. I think actually in this case it's like 0 everywhere. So that's a good sign. It's not completely self-destructing. So let's just have a look, because I got asked to compare it with Unicorn. So let's have a look at Unicorn now. That's pretty bad. What happened there? That is, I don't really know how to interpret this. Obviously, there's a ton of errors. I noticed this actually. I don't know if it's somehow that work is interacting with Unicorn or just something wrong with Unicorn. But, and I haven't spent that long benchmarking it, so just take this with a grain of salt. But those numbers are atrocious. You know, it's just so low for some reason. So if we just have a look at like that number, that's kind of a midpoint. 37,000 requests per second. You know, Puma was between 29 or 17 and 29,000 requests per second, and Unicorn's down there with like 271. I don't know what's going on. The latency's not that bad, but it's not serving many requests, so yeah. So there is another benchmark which is pretty interesting. I want to look at the code for the benchmark. It's this one here called non-blocking. And basically, oh no, beer bubbles. Once I had a drink, I spilled over a glass of tea, a cup of tea, and it went through my desk and it dripped onto a power amplifier. And the power amplifier started, it was still playing music the whole time. It started arcing though, because it let the tea went into the power supply onto the rectifier or something, I don't know. It's such a beefy old power amplifier, it just kept on going. But I love it so much I ripped the plug out and it was actually all okay, like it, despite having a whole bunch of water tipped on it. It was actually fine. That was very surprising. I thought it had blown up. Alright, back to the code. So when we're running in Falcon with Async, it just uses the async sleep method, otherwise use kernel sleep. And you might think this is a bit of a hack, and you're not wrong, but there's no reason why kernel sleep can't just call this function with the right, with the right hooks. So, this is really to look at scalability of async versus threads without any kind of async model, event-driven model, I guess is a more logical one to call it. So let's just come back here and have a look at the results. I'll just switch all of this off. Right, so Falcon does that. It just has this kind of nice curve, which is eventually going to flatten out, but it pretty much keeps on going up. It's actually sleeping for 10 milliseconds? Yeah, 10 milliseconds. So the latency, that line there, that's 10 milliseconds. And so we do hover around that. We get up to 8 in here, so it's looking like, of course, at some point there is processing going on that is impeding the ability of those requests to be serviced. And then 0 errors across the board there. Passenger, yeah, let's just not go there. It's very disappointing. Puma looks like that. So up until 8 processes, it's identical to Falcon, but once we get past that, it stays at what it can handle at 8 processes. I don't know if I reran this with the updated latency code. Let's have a look at the latency. So the Puma latency and Falcon latency is great up until you hit the limit of 8 processes, and then it just does the same thing as before, just completely blows out because the requests are getting backed up. But Falcon, its latency is actually pretty good, like in comparison. Again, like I don't think this is quite right how it goes like this. I think it's just a problem with work. And then let's have a look at Unicorn. Where does Unicorn? Okay, no, let's not bother with it. There's no point. So I think that ultimately, I guess the benefit of the async approach is that you kind of avoid some of these edge cases. Now, I guess it could be fun just to have a quick look at what happens when you put Puma into let's try this. So we boot Puma with 8 workers, and each worker has 16 threads. So let's just let's redo that benchmark. Hold on. What do I need to do? Break Puma setup. Oh, I have to stop it first. It's going to cause even more problems. So that's shutting down the VM. I don't even think it's a VM. It's just running natively, but it's inside a container. I don't know. All that stuff is just a bit beyond me. Rig Puma setup. So that's just rebuilding the image, and it will copy across the updated systemd service file. There should be a way to tell it doesn't need an operating system, but I don't know. It still thinks it needs a kernel, so it's not actually running the kernel that it builds. Okay, and so let's run the non-blocking benchmark.
Come here, Pete. Ender dragon. Yeah, I come cry. Yeah, Pete. Pop the magic dragon. Pop the magic dragon. Oh, this is not a magic dragon. It's the Ender dragon of all of Endermans. road to another portal. Puff the magic dragon.
Is this still running?
Puff the magic dragon. As it goes flying by. Puff the magic.
So we're just going to use that
The magic dragon.
version of work we compiled.
Puff the magic dragon. Well, this is magic. Puff the magic dragon. As it goes flying by. Puff the magic dragon. As it goes flying by. Puff the magic dragon. As it goes flying by. Puff the magic dragon.
We've got some wedding music.
As it goes flying by. Puff the magic dragon. As it goes flying by. Puff the magic dragon.
So while I'm waiting for that to complete,
Puff the
what else we
magic
could talk about?
dragon. As it goes flying by. Puff
To be honest, work is not that interesting.
Puff the magic dragon as it goes flying by.
Okay, Puma might not be responding.
As it goes flying by. Puff the magic dragon as it goes flying by. Puff the magic dragon as it goes flying by.
Okay, we didn't start it.
Puff the magic dragon as it goes flying by. Puff the magic dragon as it goes floating by.
Okay, great, it's getting results. I guess while we're waiting for that to complete, let's have a look at Falcon, just since I have nothing else to really talk about. So Falcon is actually quite a small code base, relatively speaking. The the main use case right now for Falcon is for development. It's not quite in the right position for production use. I mean, you can use it in production. People are using it in production. But Falcon Serve is designed for development use, and it has certain limitations. For example, you can't specify SSH settings. It doesn't support any kind of like proxying or anything like that. But there is actually Falcon has a mode which lets it replace Nginx, so it can do things like proxying, custom SSL stuff. It can basically do like the 80% of Nginx that you care about, and doesn't do the 20% that you don't care about. So let's have a quick look at how it's organized and how it fits together and where it's going to be going next until that benchmark finishes running. So serve, Falcon serve is the main command. Actually, I'm using it over here to serve those results. This is actually coming via Falcon, which is pretty funny, I guess. Falcon is running over here, which is serving that content through a web application, which just serves up chart.js with the CSV files with some basic processing to put them into the format that's required for chart.js. So when you run this, I mean, I was already running it, but you can choose whether you want to run in like a multi-thread mode, or in a multi-process mode. And I guess the the main interesting thing about threads and forks is that as Ruby becomes more, obviously we have like C Ruby as the main implementation, but JRuby and Truffle Ruby and Rubinius, they're all different implementations. They have different trade-offs, and the JVM cannot support forks. So the multi-process model does not work as easily in JRuby as it does in C Ruby. And I guess the other annoying thing is that in C Ruby, to get the maximum performance, you want multi-process, and in JRuby, to get any kind of like good performance, you want to use multi-threads. So it's kind of tricky. Which option you choose just really depends on what platform, and I think it actually auto selects the right one depending on like whether you're running on the JVM or C Ruby. It also supports the hybrid model, which is multi-process, multi-thread, but that was kind of just an experiment. You can match Falcon and Puma, because Puma has a cluster mode which will spin up like 8 processes and 16 threads per process. And Falcon can do the same, but actually because of Falcon's event-driven model, it performs, in my benchmarks, slightly worse than Puma in that same configuration. There's not really any point to do that. You're better off having like 8 processes or 8 threads with 1 event loop per process or per thread. It just makes more sense. Right, so out of the box, Falcon supports SSL, so you might notice that even though it's completely irrelevant, this website, even though it says it's not secure, it's actually running over HTTPS, and it uses an automatically generated self-signed certificate. I think I can see that just by clicking on that. And so there's actually a gem which does that called localhost. So this is a gem I made for doing self-signed certificates. Anyone can use this, and if you do use it in your project, then when the user puts it into their web browser or other system, then any other project that uses the same localhost self-signed certificate will also be recognized. So that's kind of a nice way of sharing those certificates. And they get stored in, not in there. They get stored in there. So I have a bunch of certificates for different localhost domains that I've tested with. Coming back to Falcon. One of the things that I have wanted to achieve with Falcon, which I'm pretty close to doing, is replacing Nginx on all of my production servers. And the reason why, my main motivation for doing that is because Nginx is just such, I can think of a lot of words, but my daughter's in the room. It's not really like a fantastic thing to set up. Like, it's not exactly a pleasant set of configuration files. The defaults are all pretty wonky, and I just tend to find that I end up duplicating the configuration over and over again, and I just wish I didn't have to do that. And to me, like, most of my web applications are Ruby, so I want something that's simple. I can basically go gem install Falcon and then have all my web applications running. I don't want to have to like throw up any more configuration than that. So what I've been playing around with is in your web application, and there's some here, you have this file called falcon.rb, and this is definitely not what it's going to look like when it's finished. Don't assume that it's going to be like this, but what you do is you say load, and you give it like a list of these modules, and then you give it like a list of things you want it to do. So that in this case, we've got a rack application called bear.localhost, and it uses self-signed TLS. This one is very similar, but it runs on hello.localhost, it uses self-signed TLS, and it has a supervisor as well. Now, what we can do is I can show you. It might work. Let's see if it works. So there's Falcon Virtual, which is the virtual hosting kind of subcommand. I may need to run that as sudo. Yeah, I can't though because it's not. So there are a couple of options which will let me make this a little bit easier. I want bind and secure and bind secure. So I'm gonna bind it to ports other than the main ones. Okay, and none of the dependencies are installed. I need to go and update them. Falcon Virtual does actually use the bundle of the web application. It's quite an interesting, or quite a tricky problem to work around, but basically Falcon will run and it will fork Ruby instances which then load the bundle for the specific application. Not executable benchmark Falcon. Oh yeah, it needs to be an executable. That was the only one, right? Yeah, okay. Bin Falcon, no such file or directory. Oh, I think I had that problem before as well. Let's just do that one and that one. Oh yeah, great. Let's have a look at the process tree. Not tmux, htop. This is awfully huge. It's got all the application servers running. So here's Falcon Virtual running, and basically it's spun up one process per CPU core. The Falcon redirector, all it does is it redirects from HTTP to HTTPS. The main logic behind it is that no one should be using HTTP for anything now. It should just always be a redirect with something like HSTS or something else. So that is the default, it just will always redirect. Then Falcon proxy, these 8 application, like Falcon application proxies, will receive incoming requests and then shoot them off to one of the specific application servers. Each individual application spins up one process per CPU core, and one of them has a supervisor running and one of them doesn't. The supervisor is a process which can do things that will tell you about the application server. So let's go and have a look at that quickly. Let me just check how we're doing with the benchmark, because I must be getting pretty close. Oh, come on. I should really make that the default. Oh yeah, we have some more time. So, in here is this file called supervisor.ipc. Server.ipc is the socket that all the application servers are listening on, or service requests for this particular application. Falcon supervisor tells you stuff about the processes. process ID, memory, CPU, virtual memory, how long it's been running for, and the name of the command. It's not that exciting right now, but the plan is to include additional stats in there, and it's just all controlled through this file here. It doesn't run in process, in the sense that it's still communicating with all those other processes to figure this stuff out. In fact, this one is actually just using PS. It's not even that elaborate. And then it supports the ability to do restarts. Falcon is pretty bulletproof anyway. If we take like a process ID, let's just put that there, put that there. So I just killed that application server process, and you can see it spun up a new one instantaneously. It's pretty cool. And let's just have a look at so they just restart all those 8 processes. It was probably too quick. So you can use that as part of your deployment to restart the application server. Yeah, so what does this mean? So the whole point is that you just make these falcon.rb files for all the application servers, and your startup script just looks like Falcon virtual star, wildcard / falcon.rb, and then it will just start up all your applications. And so they're running, and if I bring up a web browser, they're all using self-signed TLS. I can go to, what was it beer at localhost? I can't remember which one I started. I thought I started beer. Oh, sorry, it's running on port. Right. So we can go to the redirector. I can show you that that's working. Right. And then it redirected through to the secure version. And that is the bear example, which is a streaming example. It runs straight through rack, but it can stream the response. So I think it's pretty cool. So it certainly can replace Nginx. It supports HTTP1, HTTP2, HTTPS, supports Ruby web applications. In theory, it's more scalable than Puma, but I'm sort of, I'm optimistic, but I think more testing is required. There's definitely some edge cases where latency can be an issue. With HTTP2 in particular, it's just a completely different set of kind of, the behavior changes quite a bit. And so let's have a look. How are we going for these stats? Oh, it's going to take forever. Well, I'm kind of like, I'm done with this talk. So all I really want to show with these stats, and I might post some screenshots later on Twitter, but what you'll see is that we had a cluster of, there was 8 machines times 16 threads, which is 128, and each request was 10 milliseconds. So that means we should, in theory, have to do 100 requests per second. So we should have to do like 12,800 requests per second with no impact to latency. And then beyond that, if you add one additional request, that request will have twice the latency, because we'll have the latency of one of the requests that's currently running plus the latency of itself. And I think that's kind of the nature of how that server works. There's nothing wrong with it. But I wanted to show that on a graph, but I can't be bothered waiting, so we'll leave it there, and I'll put some screenshots up on Twitter. It's not that different, but just 8 just moves along to 128. Basically, you'd see this line here, and it would. Yeah. So Puma would probably get to like to there. It might even get higher. Who knows? Puma when it's like not saturated, potentially could be better. So. Anyway, let's leave it there for now. If you have any questions, feel free to hit me up on Twitter.